Hi everyone, my name is Qingyu. It's an honor to present our work here, and our work is named as End-to-End Semantic Segmentation and Boundary Regularization of Buildings from Satellite Imagery. And this is a work collaborated with Technical University of Munich, German Air Space Center, and Graz University of Technology. The existing semantic segmentation networks seem to be able to deliver very promising segmentation results for the purpose of building footprint generation at large scale. However, when we zoom in some segmentation masks, it can be clearly seen that such results are not that perfect, since there is no constraint on the geometry of the extracted building footprints. Moreover, the extracted building footprints have irregular shapes. Recently, a deep learning-based methodology has been proposed to deal with this issue. They perform the building segmentation as the first step and then apply the building regularization as the second step. However, when we apply this method on the planet satellite imagery, the results are not so good. The reason is that the spatial resolution of planet satellite imagery is 4.77 meters, which is a coarse spatial resolution, and the depth of the encoder in the generator is so deep that it cannot fully recover the details of the buildings at such spatial resolution. Moreover, this framework is two-stage. Actually, an end-to-end training scheme is preferred in our research, as it can provide more replicable and stable building footprint maps, especially for large-scale applications. Therefore, the motivation in our research is that we want to develop an end-to-end framework to directly get regularized building footprints from the planet satellite imagery. This figure provides an overview of the proposed method, which consists of two modules, the generator and the discriminator. An encoder-decoder structure is implemented in the generator, and there are two parts in the generator, the regularization part and the reconstruction parts. The former takes the satellite imagery as the input and produces the regularized building footprint masks from the encoder E1 and the decoder F. At the same time, the latter encodes and decodes the ideal input mask by the encoder E2 and decoder F, ensuring to have the same real-valued masks at the input to the discriminator. Then, two discriminators D1 and D2 are introduced in order to distinguish between regularized footprints and ideal ones at different scales separately. This can assure better discrimination, and it should be noted that the whole network is trained in an end-to-end fashion. This shows the objective function of the proposed method. Well, it consists of two parts, the loss of the generator and another part is the loss of discriminator. The goal of the generator is to learn a mapping function from the satellite imagery Z to ideal building footprints Y, and is learned with three types of loss functions: adversary loss, reconstruction loss, and semantic loss. In this research, planet-scope satellite imagery with three bands red, green, blue at 4.77 spatial resolution is selected as the experimental dataset in order to fully harness the high-level details of OpenStreetMap and assure that reconstruction parts Being capable of recovering all those fine details, we firstly resample the satellite imagery to 0.75 meter spatial resolution, and then rasterize the corresponding building footprints from OpenStreetMap to the same spatial resolution. Afterwards, satellite imagery and their corresponding ground reference are cut into patches with a size of 256 by 256 pixels. The number of training and validation patches covering 4 European cities are shown in this table, which including Berlin, Cologne, Milan, and Zurich. And for the test, the model of we select 1,600 patches from Munich. In order to validate the superiority of our methods, we select two methods for comparison. One is FC-DenseNet. It's a semantic segmentation network. Another is called two-stage. It is a boundary regularization network. And in this method, FC-DenseNet is exploited to perform the initial semantic segmentation of buildings. And then this result is further processed by the regularization network to generate the structure building footprints. And here we can see the statistic results of different methods, and the performance of all models is evaluated by four metrics: F1 score and intersection over union IOU for mask metrics, while similarity index metric SIN and the F measure are used to measure the quality of building boundaries. And from the statistics results, we can say that our method outperforms FC-DenseNet and two-stage in terms of mask and boundary accuracy. Then we can say the visual results. And from these figures, we can see that our method is able to increase the quality of building boundaries without losing mask accuracy. For the conclusion of our research, in this paper, we have proposed a novel boundary regularization approach that obtains building footprints based on a generative adversarial network model. And the experiment's results have demonstrated that our method is more competitive when compared with the state-of-the-art semantic segmentation and boundary regularization methods. On the one hand, the building boundaries provided by our method are more fine-grained, and the regular shapes of buildings are better preserved. On the other hand, the accuracy metric of building masks provided by our method are also improved. Thanks for listening.